Hey friends, it is Ben again. I might get a cell phone call during this or something. If so, apologies. But somebody asked me, could I go ahead and work out the thing that y'all were needing to set up on exercise 5 so that you could see what was going on with it. So I've got that worked out for y'all. It's using some GeoGebra, a little bit of animation to help us see what's going on. But I think it's helpful to see a little bit more about what's going on with exercise 3 because it'll help you with the visualization on exercise 5. Okay, so bear with me a little bit here and we will see what gets done on this. So let's see, start with the iPad. And so I need to turn the iPad on, huh? So share from the iPad. All right, so here is exercise 3. We did get some or all of that done in class, but the notion is that you're looking at a volume between two surfaces. So what we need to do is to be able to visualize the surfaces. In theory, you look at this and you recognize that that is one of the paraboloids that we've looked at previously. And so you have that sort of idea in mind. It's a paraboloid opening up. Now this part here, you'd see that you've got a constant, so it's shifted up or down or something, and you've got -3 times the x squared and the y squared. So that ought to give us an idea that if this one's like a rotation of a parabola opening up, this one will be like a rotation of a parabola opening down. Okay. So playing musical windows here for a minute. I hope it doesn't make any of y'all nauseous, but we're looking here, except I did not leave it on the right tab. And that is always a trial with these. Yeah, here we go. All right, so this is what we were looking at there. Notice here's the 36 minus 3 x squared minus 3y squared, and here's the x squared plus y squared. So the purple one is the opening down, and the blue one is opening up. And then if you look, you can see that they intersect there somewhere, and it's above the XY plane. But because we want a surface that's between those two things, then we need to think about where they intersect at. And let me see whether I've got that. Yep, I've got that. So if you look here, you've got the equation 36 minus 3x squared minus 3y squared equals x squared plus y squared. If I zip out there a little bit, you can see that those will intersect in a circle. And that's algebra you can totally do yourself. You can take the 36 minus 3x squared minus 3y squared equals x squared plus y squared, move the 3x squared and the 3y squared over so that you'll have a 4 times x squared and a 4 times y squared, divide everything by 4, and you have that circle. Now, of course, we want where things are between those. So we actually want the region to be that whole circle. Okay. So with that in mind, jumping back to the iPad to write down what we're doing here. So we're looking at the volume that's between these. I'm going to write it with a triple integral, 1, 2, 3, and dv, which, yeah, actually I should have written that first. So let me go ahead and write integral, integral, integral across the region dv. And then we're going to set up our integration. And we want to write down what our dv is. But because everything was circles, we're going to say r dz dr d theta. Okay. So with the d theta, oh gosh, let me go ahead real quick and just draw that again so that we can see it here. We had our circle, and what would the radius turn out to be? 3. So we write r equals 3 there. And we will think about that we are going one rotation around, so we can go 0 to 2 pi. You could have it with different ranges there, but it just essentially needs to have that period appearing in it. And then we think about starting here at the origin, and any particular theta value, doesn't matter which one, but we need the idea in mind that it could be any of them. And you start at r equals 0 and go out. So you enter the region where your r is 0, and you exit where your r is 3, okay? And then if we go back to that picture, the bottom of the two surfaces was the x squared plus y squared, which is really z equals r squared. And the top of the two surfaces is the 36 minus 3r squared, okay? And now we can go ahead and do the integration here. Notice that the limits on your theta and your r are both constants, but your z, it's not a constant. So with respect to the z, we have to go ahead and actually do that integration. So, well, we'll have to do it in the other place as well, but we'll be able to skip a little bit of work. We'll have r, and we'll integrate dz, so we'll get z, and the z goes from r squared to 36 minus 3r squared, dr d theta. So integral 0 to 2 pi, integral 0 to 3, r times, now if you go ahead and plug in there, 36 minus 3r squared, and then minus another r squared, you can see that it'll simplify pretty nicely there. And I'm going to go ahead and put it all together and have the 36r minus 4r cubed dr d theta. The nice thing I was hinting at there is that you can go ahead and turn this into a product because your limits of integration are constant, and you can factor it into a function with just r's and a function with just thetas. Of course, the one with just thetas is only 1 d theta, so that integration is super easy. It's just going to be the width of the interval. But then with the other one, you've got to go ahead and do a little bit there. You have 18r squared minus r to the 4th, evaluate 0 to 3. So when you plug in there, you have 2 pi times 18 times 9 minus 3 to the 4th, 81. And I am going to step off to the side and multiply and subtract because it's the end of the day and I can't quite manage it. So I end up with 162 pi if I entered that into the calculator right. Okay. So the main thing that I wanted you to get there was this notion that we had on the other screen. Is it? Yeah, here. Which was that we took a look at the three-dimensional object and we figured out where the two three-dimensional objects intersected at. Intuitively, and we saw that the region we wanted was above, the solid we wanted was above a certain region that we projected down into the XY plane, and we figured all that out. Now, our one that we're going to look at for number 5 is a little bit different, okay? So let me go ahead and show you that. And it's right here. Okay, so the question said to find the average height of the shape as z is less than or equal to h minus x squared minus y squared above the xy plane. Okay, so we're going to get a graph of that going. And the trick is when we want to graph h minus x squared minus y squared, h isn't a number. Well, okay, it's, yeah. I don't want to get super philosophical about this, but you know that old thing about this is not a pipe. I hit the wrong share screen, sorry. That h represents a number, but it's a number that you have to, oh, come on. I hate it when this does it every damn time. Sorry. That h is going to be a number, but it's not a number that's just like sitting there like 4. So what I've done on GeoGebra here is I made a slider with the h values going like from -1 to 8, because I figured that'd be good enough to give us the idea. And then I wrote the function f of x y to be h minus x squared minus y squared, like we saw in the problem. And then I did something else here that I'll talk about in a second. But what I wanted to do was to see what happens here as we have that object, that paraboloid, pushing up through the xy plane. And because we were talking about the z's that are below that, but above the xy plane, then we have to think about all the stuff that's under the surface. And of course, the place that it actually hits that xy plane is going to be a circle. And I went ahead here and told this to draw the circle using a parameterization. And you don't have to do that portion of it, you know, but you can do this visualization that whatever h is, I'm going to end up with a circle that has a radius of square root of h. And the way that I see that is by taking h minus x squared minus y squared and setting it equal to 0, okay? And so we will get that circle again. So if I go back to the iPad and do a quick bit here, then I know that I want to talk about a circle with a radius being square root of h. I'll just draw that super quick here and write r equals root h, okay? And I'll think about setting up my integral, but what I need to do here to get my average value is to take 1 over the area of my region of the double integral across that region of my function f of xy. Okay, so if we were doing this for a function of one variable, we would take and do the 1 over b minus a integral a to b f of x, comma y there, but f of x dx. Okay, that's the one-dimensional version of it. But since we've got the two-dimensional version, we have a little bit more to do. Now, fortuitously, we know the way to get the area of a circle, right? So area equals pi r squared, but the r that we're worrying about is the square root of h. So we get pi times h, okay? So 1 over pi times h. And then we have to do our integral, and the integral of the function h minus, it's a circle, so we're going to say h minus r squared dA will be r dr d theta. And the setup for the circle is just to go from 0 to the square root of h, and then from 0 to 2 pi on the d theta part. Okay. So when we're doing that, 1 over pi h stays at the front. We can see that we've got an integral, or two integrals that both have constant limits of integration, and we can factor out the thetas because there aren't any, right? So we can get the 2 pi from the integral from 0 to 2 pi, and then do the actual integration there and have 1/2 h r squared minus 1/3, and now not 1/3, sorry, 1/4 r to the 4th. That's because the r squared times that r is going to be r cubed, and you're integrating it and getting the power to go up by 1. We're going to plug in 0 and the square root of h, and we will do what we can here for simplification. I'm going to leave my canceling off till the end because it kind of all falls out at once. And so it's kind of nice. So the square, when you plug in square root of h to r squared, you'll get just h minus 1/4. And when you put the square root of h to the 4th power, you'll end up with an h squared. So now, if I continue to put that off a little bit, I end up with a 1/4 h squared here. And so I can come along and cancel my pi's, cancel one of my h's, and cancel a little bit there. And we end up with a final answer of just h over 2, which is pretty neat. Okay. But the main thing for you to spot there is that visualization about your paraboloid that's opening downward there. And when we change the h value, all we're really doing is moving it up or down. So then when you want to see where it's intersecting the z equals 0, the xy plane, you're setting the z equal to 0 and solving. And so you get a circle of radius square root of h. Okay, yeah. None of that was super duper easy. I totally get that, but I'm always trying to sound comforting. So if it sounds like I was being dismissive, I'm just trying not to scare people. So, rah. Okay. Anyway, thanks a lot. I will see you all in class.